The universe begins with a problem so severe that, on paper, it should have erased itself before it ever had the chance to become anything at all. Not later, not gradually, immediately. In the first moments after the Big Bang, reality was hot beyond imagination. Energy was packed so tightly that space itself behaved like a furnace capable of turning light into matter. Particles and antiparticles appeared in pairs, born from energy, identical in every way except one. One carried positive charge, the other negative. One was matter, the other antimatter. This was not chaos. It was symmetry. Every electron had a mirror partner. Every proton faced an antiproton. Nature, at its most fundamental level, seemed to prefer balance for everything, an equal opposite thing for every existence, a built-in eraser, and that eraser worked perfectly. When matter meets antimatter, they do not clash or collide in a conventional sense. They vanish. Their mass is converted entirely into energy, released as light. No debris, no leftovers, just a flash. And then nothing where something once was. Now pause here. If the universe truly began with equal amounts of matter and antimatter, then every particle should have found its opposite. Every atom should have met its mirror. Every structure should have cancelled out. The result would not be emptiness in the way we usually imagine it. There would be no stars, no galaxies, no space quietly stretching in the dark. There would be only radiation thinning endlessly. A universe that burned itself out before it could even cool down. A universe without chemistry, without planets, without observers. A universe where this sentence could never be spoken. And yet, you are here. The very fact that you exist means that something went wrong with perfection. This is the first shock. Not that the universe is large or old or violent, but that existence itself is an anomaly, a statistical accident, a deviation so small that it hides inside equations, yet so powerful that it determines everything you see, somewhere in the first fraction of a second. The universe broke its own mirror. The imbalance was tiny, almost insulting in how small it was. For roughly every billion pairs of matter and antimatter particles, there was one extra particle of matter left over. One. Not a million. Not 1,000. One. That single surplus particle had no partner to annihilate with. It survived. Then another. And another. And another. Those survivors collected. They cooled. They formed protons and neutrons. Atoms followed. Hydrogen filled space. Gravity began to sculpt matter into clumps. Then stars. Then galaxies. Everything you have ever known traces back to that leftover remainder. Every cell in your body, every mountain, every thought that has ever crossed a human mind, all of it is built from what should not have been there. This is where the story becomes unsettling. Because the universe did not need to favor matter. There is no obvious reason it should have. The laws of physics do not contain a line that says, "Let existence continue." On the contrary, their most elegant forms prefer symmetry, balance, cancellation. If symmetry had won completely, reality would be sterile and silent. Instead, reality cheats. That raises a question that refuses to stay abstract. If the universe can violate its own symmetry once, at the most fundamental level, what does that say about the nature of order itself? Is existence a rule or a loophole? At this point, it is tempting to treat the imbalance as a miracle, a poetic coincidence, a stroke of cosmic luck. But physics does not accept luck as an explanation. If matter survived, something caused it to survive. A mechanism, a process, a subtle bias embedded in the fabric of reality. And here the discomfort deepens, because the imbalance is not large enough to be obvious. It does not shout. It whispers. It hides behind decimal places and statistical margins. Detecting it requires patience, precision, and a willingness to accept answers that feel unsatisfying. This is not a mystery solved by a single observation. It is a mystery that stretches across particle accelerators, underground detectors, and decades of failed explanations. The universe presents us with the outcome first, a cosmos full of matter. Then it challenges us to reverse engineer the crime. What broke the symmetry? Was it a flaw in the laws of physics as we understand them? Was it a process that only operates at extreme energies no experiment can fully recreate? Or was it something so ordinary, so subtle, that we have been overlooking it while searching for dramatic answers? The uncomfortable truth is that modern physics can describe the universe with astonishing accuracy, yet still cannot fully explain why there is more matter than antimatter. We can calculate how particles behave. We can predict annihilation with near-perfect precision. We can even create antimatter in laboratories and watch it disappear in flashes of energy. But we cannot yet account for the original imbalance that made all of this possible. This is not a failure in the usual sense. It is a boundary, a place where our understanding thins, where equations still work but their meaning begins to slip. Standing at that boundary forces a change in perspective. You are not living in a universe that naturally produces structure. You are living in a universe that barely avoided erasing itself. A universe that balanced on the edge of nothing and leaned, just slightly, towards something. That lean was enough. It reshaped everything that followed. It set the stage for time, complexity, memory, and curiosity. It made it possible for the universe to eventually ask questions about itself, including this one: why does anything exist at all? This question is not philosophical decoration. It is a scientific demand, somewhere in the early universe. The laws of physics allowed a preference, however faint, to emerge. Understanding that preference means understanding why the universe looks the way it does. Rather than remaining a featureless bath of radiation, it also reframes your place within it. You are not separate from this imbalance. You are composed of it. Every atom in your body is a survivor of a cosmic process that overwhelmingly favored annihilation. Existence did not arrive confidently. It crept in through a crack. That crack is what we are about to follow, not to romanticize it, not to mythologize it, but to trace it carefully through mathematics, experiments, and history, until we reach the limits of what is known. Because before we can understand antimatter, or broken symmetry, or the early universe, we have to accept the starting point. The universe you inhabit should not exist, and the fact that it does means the story of reality begins not with balance, but with a flaw. To understand how close the universe came to erasing itself, you have to picture a reality built like a mirror hall. Every particle has a counterpart, not a rough copy, not an imitation, but a perfect reflection. Same mass, same lifespan, same behavior under every known force except one detail that flips sign. Electric charge reverses, quantum numbers invert. Matter becomes antimatter. This symmetry is not decorative. It is structural. The equations that govern particles do not merely allow antimatter, they demand it. If matter exists, antimatter must exist too, like a shadow that cannot be separated from the object casting it. In this mirror universe, creation happens in pairs. Energy condenses into an electron and a positron. A quark appears with an antiquark. The process is reversible, immediate, and relentless. As soon as conditions allow, light becomes matter. As soon as matter meets its mirror, it turns back into light. Nothing about this is unstable or exotic. It is ordinary physics at extreme temperatures. It is symmetry doing exactly what symmetry is supposed to do, and that is the danger. When matter and antimatter meet, they do not negotiate. They do not leave fragments behind. Their annihilation is total. One moment there are two particles, the next there is energy racing outward at the speed of light. The mass is gone, converted completely, with an efficiency unmatched by any process humans have ever engineered. In a perfectly symmetric universe, this would be the end of the story. As the universe expanded and cooled, pairs would continue to form and vanish. Eventually, the temperature would drop below the threshold needed to create new particles. At that point, all remaining matter would find its opposite. Every last particle would be cancelled. What remains after perfect annihilation is not emptiness in the everyday sense. It is a smooth, thinning sea of radiation. No atoms, no chemistry, no complexity, just light, stretching and cooling as space expands. This is what symmetry wants. Symmetry is elegant, efficient, and merciless. It leaves no room for leftovers. This is why the early universe is so unsettling when viewed through the lens of perfect balance. Nothing about it seems designed to preserve structure. On the contrary, its most fundamental processes are optimized for erasure, and yet, reality is not erased. Somehow, when the universe cooled enough for annihilation to dominate, matter did not vanish completely. A residue remained, not because annihilation failed, but because symmetry itself failed by the smallest possible margin. The mirror was almost perfect, almost to grasp how narrow that margin is. Imagine 1 billion identical coins laid out on a table. You flip each one, pairing heads with tails, cancelling them out. After the process is complete, only a single coin remains unmatched. That lone coin is the universe you live in. Everything else was cancelled. This framing changes the emotional tone of cosmology. The universe does not feel robust or inevitable. It feels precarious, balanced on the edge of nothingness, saved not by force or intention, but by a microscopic preference that tipped the scales. This raises an uncomfortable realization. Symmetry, for all its beauty, is hostile to existence. The universe did not survive because it followed its rules perfectly. It survived because it broke them slightly, quietly, without fanfare. At this stage, it becomes tempting to attribute meaning to the imbalance, to imagine that the universe wanted to exist, that symmetry was sacrificed for complexity, that something deeper intervened. But physics resists that narrative. The imbalance does not announce itself as purpose. It behaves like a bias, a small statistical preference, a subtle violation embedded somewhere in the laws that govern particles and time. The problem is that symmetry breaking of this kind is not easy to find. When physicists test the behavior of particles and antiparticles today, they find overwhelming agreement. For the most part, antimatter behaves exactly as expected. It falls the same way. It responds to forces the same way. It annihilates cleanly and predictably. The mirror still works. That is what makes the mystery so persistent. If symmetry is broken, it is broken selectively. It shows itself only under specific conditions, at specific energies, over specific timescales. The universe seems to follow symmetry faithfully, except when it matters most. This creates a tension at the heart of modern physics. The equations insist on balance. The universe insists on survival. Somewhere between those two demands lies a process we have not fully captured. It is not enough to say that symmetry broke. The question is how. Was the mirror flawed from the beginning? Built with a tiny imperfection that only reveals itself under extreme conditions? Or did symmetry emerge first, only to be violated later as the universe evolved through rapid transitions? These are not abstract questions. They determine whether the imbalance is a feature of fundamental laws or a consequence of cosmic history. If the mirror was flawed from the start, then the universe carries an intrinsic bias. Reality is asymmetric at its core. If the mirror broke later, then existence is the result of timing, circumstance, and irreversible processes. Both possibilities are unsettling. The first suggests that the universe is not as clean or elegant as we often imagine. The second suggests that existence depends on fleeting conditions that might easily have gone another way. Either way, symmetry is no longer a comforting principle. It becomes a warning. Perfect balance leads to cancellation. Structure requires imbalance. Complexity depends on violation. This reframes how you think about order. The universe is not orderly because it is symmetrical. It is orderly because symmetry is broken in just the right way, and that realization forces a shift in perspective. You are not living in a universe stabilized by harmony. You are living in one stabilized by a tiny unfairness, a preference so small it vanishes into the background of most experiments, yet so consequential that without it, nothing you recognize would exist. The mirror did not shatter, it cracked, and through that crack, reality escaped. Understanding that crack where it is, how it formed, and why it persists is not a decorative problem at the edges of physics. It is central. It determines whether the universe you inhabit is a natural outcome or a fragile exception. Before any history, before any experiment, before any theory, there is this simple fact. If the mirror had been perfect, there would be no one here to notice. Symmetry almost won, and that almost is the reason everything else followed. The number that saved the universe is almost embarrassing in its smallness. Not a dramatic constant, not a cosmic force, just a ratio. Roughly one extra particle of matter for every billion particle-antiparticle pairs. That is all. After the universe cooled enough for annihilation to dominate, almost everything vanished. Matter met antimatter, pair by pair, converting mass into light with ruthless efficiency. The process was so complete that what remained feels less like a victory and more like a clerical error, a remainder. That remainder is the universe, you know. To understand how strange this is, forget galaxies for a moment. Forget stars. Shrink the scale down until it becomes uncomfortable. Imagine a room filled with 1 billion perfectly matched pairs of objects. Every pair cancels out, disappears, leaves no trace. When the process is finished, you expect the room to be empty. Instead, you find one object sitting alone on the floor. That single object becomes everything. It becomes hydrogen, then helium, then clouds of gas collapsing under gravity. It becomes stars igniting, dying, and seeding heavier elements. It becomes planets, oceans, chemistry, memory, and thought. The universe did not need a large imbalance to build complexity. It needed only enough matter to avoid zero. This reframes scale in a disturbing way. We are accustomed to thinking of importance in terms of size or power, but here, significance is carried by a discrepancy so small it hides behind 9 zeros. The universe's entire future depended not on dominance, but on survival, and survival was barely achieved. What makes this even more unsettling is how clean the annihilation was. There were no partial leftovers, no fragments clinging to existence. When matter and antimatter met, they vanished completely. The energy released did not later condense into new matter in equal measure. The universe had already crossed a threshold. Creation had slowed. Cooling had set limits. This timing mattered. If annihilation had occurred slightly earlier, when energies were still high enough to recreate pairs efficiently, the imbalance would have been erased. If it had occurred slightly later, the universe might have retained more matter than it did. Instead, annihilation happened at exactly the moment when the universe could not easily undo its own losses. This is where chance begins to feel uncomfortably close to necessity. The leftover matter was not protected. It was not chosen. It simply happened to exist when the rules changed. The universe expanded and cooled just fast enough to freeze the imbalance in place. From that point on, gravity took over. Gravity does not care about symmetry. It only cares about mass. Whatever matter survived was enough to begin the long process of clumping. Tiny density variations grew. Gas clouds formed. The first stars ignited hundreds of millions of years later, powered by nuclear reactions that would have been impossible without that initial surplus. Every step in cosmic history amplifies the same fragile fact. There was something instead of nothing. This is why the 1 in a billion ratio refuses to feel trivial. It is not merely a number. It is a boundary between two radically different universes. On one side, a cosmos filled with structure. On the other, a smooth, fading bath of radiation with no memory, no observers, no questions. The difference between those universes is not dramatic. It is microscopic. This challenges how we think about inevitability. When people say the universe was destined to form stars and galaxies, they often imagine a robust process unfolding naturally. But destiny, built on a 1 part in a billion surplus, feels less like inevitability and more like balance on a knife edge. It suggests that the universe you inhabit is not the default outcome of physical laws. It is a special case. That realization carries weight, because if such a small imbalance can determine everything, then understanding its origin becomes more than an academic pursuit. It becomes the key to understanding why reality exists in this form at all. At this point, it is tempting to assume that the imbalance must be written clearly into the laws of physics, something explicit, something we have already found. But this is where the problem deepens. The known laws do allow for small asymmetries. They permit certain violations. But when physicists calculate how much matter these violations should produce, the numbers fall short. The math predicts a universe with far less matter than we observe. In other words, even after accounting for everything we currently know, the leftover is still too large. The universe kept more matter than our best explanations can justify. This is not a rounding error. It is a persistent mismatch between theory and observation. The 1 in a billion surplus is not fully accounted for by the mechanisms we have measured. That gap is where the mystery lives. The imbalance feels simple when described in words. 1 extra particle per billion. But explaining how that surplus emerged, survived annihilation, and dominated cosmic history turns out to be one of the hardest problems in modern physics. The universe does not give us a clear signature. It gives us an outcome and asks us to reconstruct the cause. This reconstruction forces humility. The story of existence does not begin with grandeur or inevitability. It begins with survival against overwhelming odds, shaped by timing, temperature, and subtle biases hidden deep in physical law. You are not the product of abundance. You are the product of scarcity. Every atom in your body traces back to a moment when annihilation almost completed its work. When the universe came within a hair's breadth of erasing itself entirely, that nearness matters. It reminds us that reality is not guaranteed. That complexity is not the natural resting state of the cosmos. It is something that had to be allowed, barely, to happen. And that changes how you see scale. The immensity of galaxies does not contradict the fragility of their origin. It amplifies it. The larger the universe becomes, the more astonishing it is that it began with so little to work with. The 1 in a billion leftover is not just a number from the early universe. It is a lens through it. The cosmos looks less like a machine executing a perfect plan and more like a process that nearly failed, then slowly recovered, building everything from the smallest possible margin. That margin is still with you, not as a historical curiosity, but as the material of your own existence. You are not standing on solid ground. You are standing on a remainder, and the question that now presses forward is unavoidable. If this leftover shaped everything that followed, then what created it in the first place? That is where the story becomes less comfortable and far more revealing. Before antimatter was ever seen, before it left tracks in detectors or vanished in flashes of light, it existed in a place that feels almost unreal. It existed in an equation. In the late 1920s, physics was undergoing a quiet crisis. The quantum world had revealed itself to be strange, probabilistic, and deeply counterintuitive. At the same time, Einstein's relativity had rewritten the meaning of space and time. The problem was that these two revolutions did not fit together cleanly. Physicists needed a new language, one that could describe particles moving close to the speed of light without breaking the rules of quantum mechanics. Paul Dirac took on that challenge. What Dirac was searching for was not a prediction of new matter or a bold philosophical statement. He wanted consistency, an equation that behaved properly, one that respected both quantum uncertainty and relativistic symmetry. What he found instead was a ghost. When Dirac wrote down his equation for the electron, it worked beautifully. It predicted the electron's spin. It explained its magnetic properties. It fit the data with unsettling elegance. But hidden inside the mathematics was something else. The equation did not produce one solution for the electron's energy. It produced two, one positive, one negative. At first, this looked like a mistake. Negative energy made no physical sense. An electron with less than zero energy should cascade endlessly downward, radiating energy without limit. The universe would be catastrophically unstable. Dirac could have dismissed the extra solution as a mathematical artifact. Many would have. Instead, he took the equation seriously, more seriously than intuition. He asked a question that feels almost reckless in hindsight. What if the equation is right? If the math is correct, then negative energy states must mean something physical. Dirac proposed an audacious idea that the universe already contains a sea of invisible negative energy electrons, completely filled, preventing ordinary electrons from falling into those states. A vacancy, a hole in this sea, would behave like a particle with the same mass as an electron, but opposite charge. Not a metaphor, not a trick, a real particle, the electron's mirror. At the time, this sounded absurd. Physics had never encountered such an object. There was no experimental hint that it existed. Dirac himself was uneasy with the interpretation, but he trusted the equation more than his comfort. This is the moment where physics takes a turn that still feels uncanny. A piece of mathematics, written to solve a technical problem, was now insisting that the universe contained something no one had ever observed, a ghost particle. For a few years, the idea floated in an uncomfortable space between theory and speculation. Some physicists tried to reinterpret the negative energy states. Others attempted to modify the equation to eliminate them. But every attempt to tidy the math weakened its success. The ghost refused to leave. What makes this episode so important is not just that antimatter was predicted before it was found. It is how it was predicted. There was no telescope pointing into deep space, no detector registering strange flashes. There was only a demand for internal consistency. The equation said symmetry required a mirror. If matter exists, antimatter must exist too. This moment marks a shift in how knowledge about the universe is formed. Reality is no longer discovered only by looking outward. Sometimes it is uncovered by listening carefully to mathematics when it insists on something uncomfortable. Dirac's proposal carried an implicit warning. The universe may be stranger than what observation alone suggests. There may be entities that exist not because we have seen them, but because the structure of physical law leaves no room for anything else. Still, the ghost remained unproven. The idea of antimatter hovered at the edge of belief. It was elegant, yes, but elegance is not evidence. Physics demands contact with the real world. An equation can suggest possibilities. Nature decides which ones exist. That tension between mathematical beauty and experimental proof defines the next phase of the story. It is easy, from a modern perspective, to treat Dirac's insight as inevitable. But at the time, it required an unusual kind of restraint. He did not rush to explain away the unwanted solution. He did not add assumptions to protect intuition. He accepted that the universe might include something profoundly unintuitive. This attitude matters. Many of the most important advances in physics come not from bold predictions, but from the refusal to ignore what the equations are quietly saying. Dirac's ghost was not conjured by imagination. It was cornered by logic. And yet, logic alone was not enough. For years, antimatter remained hypothetical, a mathematical necessity without a physical footprint, a solution waiting for reality to acknowledge it. This waiting period is often overlooked, but it reveals something crucial about how science progresses. New ideas are not immediately embraced, even when they are mathematically sound. They must survive skepticism, alternative explanations, and the slow grind of experimental verification. Dirac himself did not campaign aggressively for antimatter. He allowed the idea to stand on its own, vulnerable to refutation. That restraint gave the concept credibility. If antimatter existed, it would reveal itself. If not, the theory would need revision. The universe eventually answered, but before that answer arrived, something subtle had already changed. The boundary between mathematics and reality had blurred. Physics had crossed a line where equations were no longer just descriptive tools. They became exploratory instruments, capable of reaching beyond observation and pulling unseen aspects of the universe into conceptual existence. This is why the prediction of antimatter feels different from earlier theoretical insights. It was not inferred from patterns in data. It was demanded by symmetry and consistency. The universe was being asked to conform to logic or expose the limits of that logic. That confrontation is still ongoing. Every time physics uncovers a discrepancy, every time an equation suggests something that has not yet been observed, Dirac's ghost reappears as a reminder. The universe does not owe us intuitive answers. It owes us coherence. Antimatter began as a requirement for coherence. Before it was real, it was necessary. Before it was seen, it was unavoidable. And that makes its eventual discovery more than a confirmation of theory. It marks a moment when mathematics reached into the unknown and pulled back something real. The universe had been hiding a mirror all along. The next step was to see whether that mirror truly existed, or whether the ghost would fade when confronted with experiment. It did not fade. It left a track, and that track would change physics forever. Antimatter did not announce itself with fireworks. It arrived quietly, as a curve in mist. In the early 1930 seconds, physics was full of bold ideas and fragile expectations. Equations were racing ahead of experiments, and many theorists were cautious. A prediction was not a discovery. A solution on paper was not a particle in the world. Dirac's ghost still hovered in an uncomfortable space between logic and belief. Then, in 1932, the universe left a mark high above the Earth. Cosmic rays constantly rain down from space. They strike the upper atmosphere and shatter atoms, producing showers of secondary particles that cascade toward the surface. These particles were poorly understood at the time, but physicists knew they carried clues about nature at energies far beyond what laboratories could create. To catch them, researchers used cloud chambers. A cloud chamber is a simple but elegant device, a sealed volume filled with supersaturated vapor. When a charged particle passes through, it ionizes the vapor along its path, leaving behind a thin line of droplets. The particle itself remains invisible. Its trajectory becomes visible instead. This is where the universe wrote its answer. While studying cosmic rays with a cloud chamber placed inside a magnetic field, a young physicist named Carl Anderson noticed something strange. Among the familiar tracks left by electrons, there appeared a line that curved the wrong way. The curvature mattered. In a magnetic field, charged particles bend. The direction and tightness of that bend revealed two things at once: the sign of the particle's electric charge and the ratio of its mass to its charge. Electrons curve one way, protons curve another. This track curved like an electron, but in the opposite direction. It carried the same mass as an electron. It moved like an electron, but its charge was positive. At first glance, the observation seemed trivial. A single track, a momentary anomaly, the kind of thing experimentalists are trained to doubt. Instruments can mislead. Plates can be misread. Nature enjoys fooling the unwary. Anderson did not rush to announce a discovery. He checked the setup. He examined the magnetic field. He verified the calibration. He compared the track to known particles. The line refused to change its story. It was not a proton. Protons are far heavier, and their tracks curve differently. It was not a fragment or an artifact. The curvature, energy loss, and behavior matched only one possibility: an electron's mirror. The ghost had left a footprint. What makes this moment so powerful is not just that antimatter was observed, but how it was observed. There was no dramatic explosion, no new machine built for the purpose. The discovery came from paying close attention to something subtle and refusing to explain it away. A single curved line in vapor overturned skepticism. With that track, antimatter crossed the boundary from theoretical necessity to physical fact. The positron, as it came to be known, was real. It could be created. It could be detected. It could annihilate with ordinary matter exactly as predicted. Dirac's equation had not been hallucinating. This discovery forced a reorganization of reality. Matter was no longer alone. The universe contained a mirrored counterpart, hidden in plain sight, appearing whenever energy allowed it. The symmetry that once threatened to erase existence was now undeniable. And yet, this did not resolve the deeper mystery. If antimatter exists, and it clearly does, then the early universe should have produced it in abundance. The same processes that create electrons create positrons. The same forces that bind quarks bind antiquarks. There is no preference in the basic interactions for one over the other. The positron's existence strengthened the paradox rather than dissolving it. Now the mirror was not hypothetical. It was real, measurable, reproducible. The question shifted from, does antimatter exist, to something far more unsettling. If the mirror exists, why did it lose? This is where the emotional tone of the story changes. The discovery of antimatter should have been triumphant. It was a victory for theory, a confirmation of mathematical insight, a celebration of symmetry. Instead, it deepened the unease, because the more real antimatter became, the harder it was to explain its apparent absence on cosmic scales. In laboratories, antimatter appears readily, then vanishes in flashes of energy. In the universe at large, matter dominates overwhelmingly. The first proof of antimatter sharpened the imbalance. It told us that the universe had every opportunity to erase itself. It possessed the tools. It followed the rules. And yet, it did not complete the task. The positron also revealed something important about how science advances. Discoveries do not always arrive wrapped in clarity. Sometimes they arrive as complications. They confirm one idea while destabilizing another. Antimatter solved a theoretical inconsistency and created a cosmological one. From that point on, antimatter could no longer be treated as an abstract concept or a speculative curiosity. It demanded explanation. Its existence made the absence of large amounts of antimatter in the universe impossible to ignore. Every experiment that produced antimatter reinforced the same uncomfortable conclusion. The universe did not lack the ingredients for cancellation. It lacked only the will, or rather, the mechanism to complete it. The cloud chamber track did more than confirm a particle. It confirmed that the laws of physics are capable of symmetry, but not obligated to preserve it in outcomes. The mirror exists, but the universe does not treat both sides equally. This realization reshapes how you think about discovery. The most important breakthroughs are not always the ones that close questions. Some open them wider. Seeing antimatter for the first time did not explain why matter survived. It made the survival undeniable. From that moment on, the universe could no longer hide behind ignorance. It had revealed the mirror. It had admitted that annihilation was possible, natural, and efficient, which leaves only one uncomfortable fact. Something intervened, not dramatically, not loudly, but decisively enough to tip the balance and let a thin residue of matter slip through annihilation's grasp. The first proof of antimatter did not end the story. It removed all excuses. From here on, the imbalance could no longer be blamed on missing physics or incomplete understanding of particles. The mirror was real. The cancellation was real. The leftover was real. And somewhere between those facts lies the reason the universe still exists. That reason would not reveal itself easily, but after that curved line in vapor, there was no turning back. Reality had shown its reflection. Now it had to explain why the reflection did not prevail. For a long time, symmetry felt like a promise. If you flipped the universe left to right, it should behave the same. If you replaced matter with antimatter and reversed certain properties, the equations insisted nothing fundamental would change. The mirror was not just aesthetic. It was supposed to be reliable. Then the mirror cracked. The break did not come as a thunderclap. It arrived as a small, uncomfortable result buried in careful measurements. No explosions, no cosmic spectacle, just a quiet disagreement between expectation and reality. The key idea at stake was simple to state and deeply unsettling to accept. If the laws of physics treat matter and antimatter exactly the same, then the universe has no reason to favor one over the other. Perfect symmetry would lead to perfect cancellation. Survival would be impossible. So physicists asked a precise question. Do matter and antimatter truly behave as perfect mirror images? To test this, they focused on symmetries that combine basic operations. One of them involves flipping electric charge. Another involves reversing spatial coordinates, like looking at the world in a mirror. A third involves reversing the flow of time. Together, these symmetries form a kind of moral code for physics. Break one, and something profound has happened. In the mid-23rd century, experiments began probing these ideas, using unstable particles that decay in measurable ways. These particles do not live long. They transform into other particles according to strict rules. If matter and antimatter are truly symmetric, their decays should be identical when viewed through the appropriate transformations. That expectation failed. In 1964, physicists studying certain neutral particles noticed something subtle but undeniable. The decay of matter did not perfectly match the decay of antimatter. The difference was tiny, but it was real, statistically robust, reproducible. Nature had shown a preference. This phenomenon became known as the violation of combined symmetries involving charge and mirror reflection. In human terms, it meant that the universe does not treat matter and antimatter as exact equals. The mirror still existed, but it was imperfect. This discovery sent a tremor through physics, not because the effect was large, but because it existed at all. A single confirmed violation was enough to change the rules of the game. Symmetry was no longer sacred. It was conditional. For the first time, physicists had proof that the laws of nature themselves could favor matter over antimatter, even if only slightly. At first glance, this seemed like the answer everyone had been waiting for. If nature prefers matter, then the survival of matter in the early universe begins to make sense. The imbalance might not be accidental. It might be built into the laws, but relief did not last long. When scientists calculated how much matter this asymmetry could produce in the early universe, the numbers came back disappointing. The known symmetry violations were far too weak. They could not account for the vast amount of matter we observe today. The mirror was broken, but not broken enough. This is where the story becomes uncomfortable again. Physics had found a real, measurable bias in nature, yet that bias fell short. It explained part of the problem, but not the outcome. Imagine discovering a leak in a dam after a flood, only to realize the leak is far too small to explain the devastation downstream. Something else must have happened, something larger, hidden, or poorly understood. This gap between effect and consequence defines the modern mystery. Nature admits to cheating, but it refuses to explain how the cheating became decisive. The breaking of symmetry also carried philosophical weight. Symmetry had long been associated with beauty and inevitability. Many believed that the deepest laws of physics would be perfectly balanced, elegant, and reversible. That belief took a hit. The universe was now allowed to be biased. History could matter. Irreversible processes could shape outcomes. The past could influence the future in ways symmetry alone could not undo. This reintroduces time as a meaningful actor. Perfect symmetry often implies reversibility. If you run the equations backward, the universe should behave sensibly. Broken symmetry allows direction. It allows outcomes that cannot simply be reversed. Matter's survival now looked less like a frozen accident and more like a historical event. Yet the discomfort remained. The asymmetry we could measure did not fully explain the matter-filled universe we inhabit. The known violations were real but insufficient. This forced a reframing of the problem. The question was no longer whether nature could break the mirror. It clearly could. The question became where, when, and how strongly that break occurred. Did the imbalance emerge during violent transitions in the early universe, when conditions were far from anything we can recreate today? Did it involve particles or interactions we have not yet observed? Did it arise from a sector of physics that rarely communicates with the matter we know? The mirror's crack pointed toward deeper layers of reality. It also changed how physicists approached symmetry itself. Instead of treating it as an unbreakable principle, they began to treat it as a clue, a guide to what might exist beyond current theories, a signpost pointing toward missing pieces rather than a final answer. This shift matters because it reframes failure. The inability to fully explain matter's dominance is not a dead end. It is evidence that the universe still holds secrets. The broken mirror is not an embarrassment. It is an invitation. You can feel the tension here. On one side, the comfort of symmetry, elegance, and closure. On the other, a universe that behaves asymmetrically, historically, and selectively. Reality chose the second option, and that choice reshaped everything. Matter survived not because symmetry was preserved, but because it was violated. The universe did not remain fair. It developed a preference, however faint. That preference did not shout. It whispered through decay rates and statistical anomalies. It revealed itself only to those patient enough to look. The mirror did not shatter into pieces. It fractured along hairline cracks, barely visible, yet cosmically consequential. Those cracks are still being mapped. They tell us something sobering. Existence is not guaranteed by beauty alone. It requires imbalance. It requires rules that bend just enough to let history take hold. Nature broke the mirror, not completely, not cleanly, but enough to let the universe escape perfect cancellation. And in that escape, everything else found room to exist. Once the mirror was known to crack, a deeper question emerged. Breaking symmetry was necessary, but it was not sufficient. Nature could favor matter over antimatter in small ways. Yet that alone did not explain how an entire universe ended up filled with matter. Preference without consequence is not enough. Bias without amplification fades into noise. So physicists reframed the problem. Instead of asking why matter survived, they asked a more practical question. What conditions must be satisfied for a universe with leftovers to exist at all? The answer did not come from observation first. It came from logic. In the late 1960s, a physicist named Sakharov approached the problem with a kind of ruthless clarity. He treated the universe like a system governed by constraints. If matter exists today, then certain things must have happened earlier, not optionally. Necessarily, he identified 3 rules, not suggestions, requirements. If any one of them fails, the universe returns to symmetry and annihilation completes its work. The first rule concerns identity. For matter to survive, the universe must allow processes that change the balance between matter and antimatter. If the total number of matter particles minus antimatter particles is strictly conserved, then no imbalance can ever grow. Any asymmetry would be forbidden. This rule sounds technical, but its implication is stark. The universe must permit violations of what looks like a basic accounting principle. Particles must be allowed to appear or disappear in ways that favor matter overall. Without this loophole, survival is impossible. The second rule concerns preference. It is not enough for matter number to change. Those changes must discriminate. The laws of physics must treat matter and antimatter differently in specific situations. Otherwise, every process that creates matter would be mirrored by one that creates antimatter in equal measure. This is where the broken mirror matters. The small asymmetries discovered in particle decays show that nature does, in fact, distinguish between matter and antimatter under certain conditions. But this distinction must be active at the right moment. A bias that exists too late or too weakly accomplishes nothing. The third rule concerns time. Even with imbalance and discrimination, the universe can still erase any advantage if it remains in equilibrium. In equilibrium, processes run forward and backward with equal ease. Gains are cancelled by losses. History does not accumulate. For matter to survive, the universe must be out of equilibrium. It must be changing rapidly enough that certain reactions freeze out before symmetry can reassert itself. In simple terms, the universe must move on before annihilation finishes the job. These 3 rules form a harsh filter: change identity, favor matter, break equilibrium, miss any one of them, and the universe resets to 0. What makes these rules unsettling is how narrow the allowed path becomes. The universe could not simply drift into existence. It had to pass through a very specific sequence of conditions, at very specific times, with very specific properties: too gentle, and symmetry wins; too slow, and equilibrium erases memory; too fair, and annihilation completes. This is not destiny, it is constraint. The rules do not tell us how the universe satisfied them. They only tell us that it must have. They are necessary conditions, not a recipe. That distinction matters. It means that modern physics knows the shape of the solution space, but not its coordinates. We know what must be true for a matter-filled universe to exist. Yet we do not know which path reality took to get there. This is why the rules feel both powerful and frustrating. They reduce a philosophical question: why is there something instead of nothing, into a technical checklist. But that checklist does not tell us which box was ticked first, or what mechanism did the ticking. The universe passed the test. That much is obvious. How it did so remains unresolved. What the rules also reveal is that existence is not robust. It is conditional. The universe you inhabit is not the inevitable outcome of generic physical laws. It is the result of laws operating in a very specific regime. Under very specific circumstances, This reframes how you think about cosmic beginnings. The early universe was not simply hot and dense, it was delicate. Its future depended on transitions occurring at the right pace, with the right asymmetries. Before equilibrium smoothed everything away, time mattered. This is where the story gains texture. Instead of a timeless creation event, the universe becomes a process with stages, thresholds, and missed opportunities. A sequence where some possibilities close forever, while others open briefly and then vanish. Matter survived because the universe did not linger. Expansion pulled particles apart faster than annihilation could catch up. Cooling shut down certain reactions before symmetry could be restored. Irreversibility crept in, locking the imbalance into place. Once locked, the surplus could grow in influence. Gravity could amplify it. Structure could form. History could begin. These rules also shift the emotional tone of cosmology. The universe no longer feels like a machine executing a blueprint. It feels like a system navigating constraints, where small differences at early times have irreversible consequences later. That perspective carries a quiet humility. Existence did not require perfection. It required conditions just messy enough to escape symmetry's grip. The rules do not romanticize this escape. They make it feel narrow and contingent. The universe did not have many chances to get it right. This raises a subtle but important implication. If these rules are truly universal, then matter-filled universes may not be common. The conditions required to satisfy all three may be rare, even in a vast cosmic landscape. Many possible universes might cancel themselves completely, leaving nothing behind to observe them. The one you inhabit is the one that slipped through, not because it was favored, but because it met the requirements. The rules for making a universe are not kind. They do not guarantee success. They merely allow it. And that allowance was enough. Everything that followed: stars, planets, chemistry. Consciousness rests on the fact that these conditions were satisfied once, long ago. Under circumstances we are still struggling to reconstruct. The rules do not close the mystery, they sharpen it. They tell us that matter's survival was neither miraculous nor automatic. It was conditional, constrained, and fragile. A product of laws bending just far enough to let history take hold. The universe exists because it obeyed the rules for breaking itself, and in doing so, it created room for everything else. To understand how the universe satisfied those rules, you have to abandon familiar scales. Seconds are already too large. Even milliseconds feel slow. The story unfolds in fractions so small that everyday intuition collapses. This is not a place where planets form or stars ignite. This is a time when the universe itself is still deciding what kind of place it will become. In the beginning, time does not flow gently. It rushes. The universe is unimaginably hot and dense. Energy is packed so tightly that distinctions between particles blur. Light is no longer just light. It constantly transforms into matter, and matter instantly dissolves back into light. Creation and destruction are inseparable. There is no empty space. Everything is everywhere. In this environment, particles do not persist. They flicker into existence and vanish again almost immediately. Electrons and positrons appear together, collide, and annihilate. Quarks and antiquarks do the same. Nothing accumulates. Nothing lasts. This is equilibrium. In equilibrium, memory does not exist. Processes run forward and backward with equal ease. If something forms, it unforms just as quickly. The universe, at this stage, has no history, only reactions. As the universe expands, it cools. Expansion is not an explosion into space, it is space itself stretching. As space stretches, energy spreads out, temperature drops, conditions change, but they do not change smoothly. The early universe passes through a sequence of thresholds. like doors that close behind it. At each threshold, certain reactions become harder to sustain. Some particles stop being created efficiently. Others decouple from the surrounding energy bath and begin to behave independently. These moments matter. At very high temperatures, the distinction between different forces becomes unclear. As cooling continues, forces separate. Interactions that once behaved as one begin to act differently. The universe reorganizes itself in stages, each one narrowing the range of what is possible. This reorganization is fast, violent, unforgiving. During these early seconds, the universe is not passively cooling, it is actively transforming. Phase transitions sweep through it, changing how particles interact, how symmetries behave, how reactions proceed. This is where equilibrium begins to fail, not everywhere at once, not completely, but enough. Some reactions slow down relative to the expansion. Others stop entirely. The universe outruns its own ability to stay balanced. This race is crucial. If expansion had been slower, reactions would have continued longer. Symmetry would have had more time to enforce cancellation. If expansion had been faster, particles might have frozen out too early, leaving a different outcome entirely. What happened instead was a narrow compromise. The universe expanded and cooled at just the right pace for imbalance to become permanent. As temperatures dropped, particle-antiparticle pairs annihilated in enormous numbers. Light flooded the universe. But once the temperature fell below certain thresholds, creating new pairs became inefficient. Annihilation continued, but replacement did not. This is when leftovers begin to matter. The universe did not stop annihilation. It simply stopped undoing its consequences. Imagine a busy marketplace at dawn. Trades happen constantly. Goods change hands, then change back. Nothing settles. As the day ends and stalls close, exchange is slow. Some trades remain unfinished. Inventories freeze in place. That frozen inventory becomes the starting point for everything that follows. In the universe, freeze-out moments play the same role. Reactions that once maintained balance fall out of sync with expansion. Whatever imbalance exists at that moment becomes locked in. This is not a single event. It happens in stages, affecting different particles at different times. Each stage leaves behind a slightly altered universe. Crucially, this process does not require large asymmetries. It amplifies small ones. A tiny preference, operating briefly under extreme conditions, can become permanent once equilibrium is lost. The universe does not need to favor matter strongly. It only needs to favor it long enough, at the right moment, before reactions shut down. This is why the first seconds matter so much. They are not merely a prologue. They are the decision-making phase of cosmic history. Once those decisions are made, they cannot be revisited. As the universe continues to cool, the violence subsides. Particle production dwindles. Matter becomes more stable. Protons and neutrons persist. Later, they combine into atomic nuclei. Much later still, electrons join them to form atoms. By the time atoms exist, the outcome is already sealed. The matter surplus is no longer vulnerable to annihilation. The window where symmetry could have reclaimed dominance has closed. At this point, the universe feels calmer, but that calm rests on choices made during chaos. What is unsettling is how little margin there was for error. The early universe did not have time to hesitate. It moved rapidly through conditions that shaped everything, then left them behind forever. You are not living in a universe that gradually chose matter. You are living in one that rushed past annihilation before it could finish its work. This perspective changes how you think about beginnings. The early universe was not a stable foundation upon which complexity was built. It was a turbulent passage, a narrow corridor where outcomes were decided under extreme pressure. Once through that corridor, the universe became forgiving. Gravity could work slowly. Chemistry could take its time. Life could emerge after billions of years. But the corridor itself was brief. The first seconds did not look like a place where anything recognizable could survive. Yet those seconds determined whether survival was possible at all. This is why attempts to explain the matter-antimatter imbalance cannot ignore timing. It is not enough to identify a preference in the laws. That preference must have acted when the universe was still capable of amplifying it. Later biases do not matter. Late asymmetries arrive after the door has closed. In these first moments, the universe was not asking philosophical questions. It was enforcing deadlines. Miss them. And existence resets to symmetry. That reality carries a quiet implication. The universe you inhabit is not the result of leisurely evolution from simple beginnings. It is the aftermath of a rapid escape from equilibrium, achieved under conditions that no longer exist. Everything, familiar space, time, matter emerged from that escape. Walking through the first seconds of time reveals something profound. Existence did not unfold patiently. It sprinted through danger and only slowed down once survival was secured. The universe did not ease into being. It outran its own erasure. There was a moment when almost everything ended, not in fire, not in collapse, but in efficiency. As the universe cooled past its earliest thresholds, creation slowed. Energy no longer arrived freely in the amounts needed to keep making particle-antiparticle pairs. The balance tipped. From that point on, annihilation began to dominate. This was not a single event. It was a phase. Matter and antimatter met everywhere. Electrons found positrons. Quarks found antiquarks. Each encounter erased both participants and replaced them with light. No residue, no fragments drifting away. Just energy spreading outward as the universe expanded. If you could stand inside that era, if such a thing were even meaningful, you would not see violence. You would see uniformity. The annihilations would be happening everywhere at once. Smoothly, relentlessly, without spectacle. This is what makes it unsettling. The Great Annihilation was not chaotic destruction. It was order doing exactly what it was designed to do. Pairs cancelled. Balance asserted itself. Symmetry reclaimed territory. The universe was becoming simpler by the second. What mattered most during this phase was not the reactions themselves, but their timing. Annihilation was effective only while particles could still find their opposites. As expansion continued, densities dropped, distances increased. Encounters became less frequent. The universe was thinning. This thinning did not stop annihilation immediately. It slowed it. The rate of erasure declined as particles were pulled farther apart by the stretching of space. Eventually, annihilation lost the race, not because it failed, because it ran out of opportunities. By the time annihilation could no longer keep up, almost everything had already been erased. What remained was not a significant fraction. It was a trace, a thin scattering of matter particles without partners. This is the moment when the imbalance stopped being theoretical. Before annihilation, the matter surplus was a statistical detail. After annihilation, it was the only thing left. Think about that transition. For a long stretch of early time, matter and antimatter existed in overwhelming numbers, constantly appearing and disappearing. The imbalance was hidden inside a sea of reactions. It did not matter yet. Then annihilation stripped away the excess, pair by pair, until only the imbalance remained. What survived was not protected by force or structure. It survived because the universe expanded too fast to finish the job. This is why the Great Annihilation feels less like a catastrophe and more like a filter. It removed almost everything and revealed what could not be erased under the conditions that followed. After this phase, the universe looked very different. Radiation dominated. Light filled space. Matter was sparse but persistent. The surviving particles were no longer being created or destroyed in large numbers. They had crossed a line from transient to stable. From that point on, matter could begin to behave differently. Protons did not immediately annihilate. Electrons did not vanish upon contact with an opposite. The environment no longer supported constant pair creation. The universe had cooled enough to lock in its outcome. This locking in matters because it introduces irreversibility. Before annihilation, the universe could move backward in a meaningful sense. Creation and destruction balanced each other. After annihilation, that balance was gone. History began to accumulate. Once the great annihilation passed, there was no mechanism left to restore symmetry. The universe could not easily recreate antimatter in sufficient quantities. The conditions that allowed symmetry to dominate were gone. This is where the sense of finality enters the story. The universe did not gradually decide to favor matter. It allowed annihilation to proceed until symmetry exhausted its reach, then moved on. What remained became the raw material for everything else. This perspective reframes the idea of survival. Matter did not defeat antimatter. It outlasted it. The universe changed faster than annihilation could adapt. That subtle difference matters. It tells us that existence did not require overwhelming preference. It required timing. Had expansion slowed even slightly, annihilation would have continued longer. More matter would have been erased. Had expansion sped up too quickly, other problems would have emerged. The universe might have frozen too early, locking in a different set of particles altogether. Instead, the universe passed through the annihilation phase with a narrow margin. That margin is written into everything you see. Every atom is a relic of the moment when annihilation lost its grip. Every structure traces back to a time when the universe became too large, too cool, and too sparse for perfect cancellation to continue. This is why the Great Annihilation deserves its name. It was not a dramatic end. It was a decisive pruning. It stripped reality down to its minimum viable content. Afterward, complexity had a foothold. What makes this phase emotionally difficult to grasp is how impersonal it was. There was no intention, no selection for life, no awareness of consequence. The universe simply followed its rules until the rules themselves changed. Annihilation did not stop because it wanted to. It stopped because the environment no longer supported it. That is how fragile the origin of matter truly is. Once the Great Annihilation ended, the universe entered a long, quiet period. Radiation continued to dominate for a while. Matter drifted, interacted weakly, waited. Gravity began to matter more than annihilation. But the decisive moment had passed. The universe had been pared down to its essentials. This is why the annihilation phase is not just a footnote. It is the event that exposed the imbalance and made it permanent. Without it, the surplus would have remained hidden. With it, the surplus became destiny. You are not the result of a creative explosion. You are the residue of an erasure that almost completed its work. The Great Annihilation was the universe asking a simple question: can anything remain? The answer was barely yes, and that barely is the foundation of everything that followed. Once annihilation stepped aside, the universe moved forward, carrying only what it could not erase. That remainder did not look like much. It turned out to be enough. At this point, it would be comforting to believe the problem is solved. Symmetry breaks. Timing matters. Annihilation freezes out. A small surplus survives. The universe moves on. On the surface, this sounds like a complete explanation. The laws of physics allow matter to exist, and matter exists. Case closed. But when physicists run the numbers, comfort disappears, because the universe kept far more matter than the known laws can justify. This is where the story turns sharply, not towards speculation, but toward accounting. Physics is unforgiving when it comes to totals. If matter survived, there must be a mechanism that produced the observed amount, not approximately, not poetically, quantitatively, and when those calculations are done carefully, the result is unsettling. The asymmetries we know how to measure are real, but they are too weak. The mirror cracks discovered in particle physics do favor matter over antimatter, but only slightly. When those effects are projected back into the conditions of the early universe, they generate a surplus that is orders of magnitude smaller than what is required to build today's cosmos. In simple terms, the imbalance we can explain would have left behind far less matter than we actually see. Something is missing. This gap is not subtle. It is not something that can be brushed aside as experimental uncertainty or theoretical nuance. It is a mismatch between prediction and observation large enough to demand attention. The known laws do part of the job. They do not finish it. This creates a strange tension. The standard model of particle physics is one of the most successful frameworks ever built. It predicts experimental outcomes with astonishing precision. It has survived decades of testing without collapsing. And yet, when asked the most basic existential question, why is there something instead of nothing, it comes up short. This is not a failure in the usual sense. The model does exactly what it was designed to do. It describes particles and interactions under ordinary conditions extremely well. But the early universe was not ordinary. It was hotter, denser, faster, and more violent than anything we can reproduce today. Processes that dominate at low energies may be irrelevant there. Effects that are negligible now may have been decisive then. The problem is that we cannot simply extrapolate our current understanding indefinitely backward and expect it to remain complete. This is where humility enters the story. Physics knows when it is guessing. The equations do not scream when they are being pushed too far. They continue to produce answers. It is up to physicists to notice when those answers stop matching reality. In the case of matter's survival, the mismatch is clear. The known violations of symmetry are not strong enough, not early enough, or not active under the right conditions to generate the observed surplus. That leaves two broad possibilities. Either the known laws behave differently under extreme conditions than we expect, or there are additional laws we have not yet uncovered. Both possibilities are uncomfortable. If the known laws change behavior at high energies, then our confidence in extrapolation is misplaced. The universe may have played by different rules during its earliest moments. If new laws exist, then the framework we rely on is incomplete. Something fundamental is missing from our description of reality. Neither option is easy. This is why the matter-antimatter problem remains central rather than peripheral. It is not a detail to be patched later. It points directly to the limits of our understanding. What makes this especially frustrating is how close we seem to be. We have mechanisms that do some of what is required. We have experimental evidence that nature is willing to break symmetry. We have a timeline that allows small effects to be amplified, and yet, when everything is combined, the result still falls short. The universe appears to be holding back part of its explanation. This situation forces a re-evaluation of how progress happens in physics. It is tempting to imagine that answers accumulate smoothly, with each discovery filling a gap left by the last. In reality, progress often exposes deeper holes. Every time physics explains a piece of the imbalance, the remaining unexplained portion becomes sharper, more isolated, harder to ignore. The problem does not dissolve, it concentrates. This concentration has consequences. It motivates experiments designed not to confirm what we already know, but to find deviations, to catch rare processes, to measure tiny differences with extreme precision, to look for behavior that should not exist if the current laws are complete. The goal is not to discard what works, but to stress it, because something about matter's survival is still resisting explanation, and resistance is often where discovery begins. At the same time, there is restraint. Physicists are wary of inventing mechanisms simply to solve the problem. The history of science is full of elegant ideas that explain too much too easily and later collapsed under scrutiny. The matter-antimatter imbalance demands rigor. Any proposed explanation must not only generate the right amount of matter, but also avoid contradicting everything else we observe. That constraint is brutal. It is easy to imagine a universe where matter survives. It is hard to construct one that does so without breaking other well-tested aspects of physics. This is why the gap persists. The known laws are powerful, but they are not generous. They do not offer free parameters that can be adjusted without consequences. Every change ripples outward. This makes the imbalance feel less like an oversight and more like a deliberate challenge built into reality. The universe allows matter to exist, but it does not make the reason obvious. It leaves a trail of clues that almost lead to an answer. Then stop. Standing here, it becomes clear that the question is no longer whether the known laws are correct. They are. Within their domain, the question is whether that domain includes the decisive moments when existence itself was negotiated. So far, the answer appears to be no. The laws we know describe a universe that can maintain matter once it exists. They do not fully explain how matter gained the upper hand in the first place. That distinction matters. It tells us that understanding the universe is not just about cataloging what exists now. It is about reconstructing conditions that no longer exist and may never exist again. The early universe left behind evidence of its outcome, but not a clear record of its reasoning. What remains is a tension between confidence and ignorance, between equations that work beautifully and a result they cannot fully justify. This tension is not a flaw in science. It is one of its most honest moments. The known laws have taken us far. They have carried us to the edge of annihilation and beyond. They have explained how matter behaves, how it clumps, how it persists. But when asked why matter exists at all, they stop just short of the answer. Not because the question is meaningless, but because the universe still has something left to tell us. Once it became clear that the known laws fall short, the problem changed character. The question was no longer whether an asymmetry existed. That much was settled. Matter survived. The universe is here. The imbalance happened. The question became where the rest of it is hiding. This is where the hunt begins. Physicists approach this problem the way detectives approach a crime with too little evidence. They work backward from the outcome. If the universe ended up matter-dominated, then there must have been a process, perhaps brief, perhaps violent, that produced a much larger bias than we can see today. That process left no obvious trace. Whatever it was, it operated early, then vanished from direct view. So the search shifts to indirect signs. One promising idea is that the asymmetry did not arise where we were first looking. Instead of forming directly among the particles that make up ordinary matter, it may have originated elsewhere and then leaked into the matter we see. This reframing is crucial. Rather than asking how matter beat antimatter, physicists ask whether something else beat its mirror first. This line of thought leads to particles that rarely interact, barely leave footprints, and pass through the universe almost unnoticed. Neutrinos. Neutrinos are among the strangest particles known. They have almost no mass. They carry no electric charge. Trillions of them pass through your body every second without leaving a mark. For decades, they were assumed to be perfectly symmetric, perfectly aloof. That assumption did not survive scrutiny. Experiments revealed that neutrinos change identity as they travel. They oscillate between different types. This behavior implies that they have mass tiny, but real, and that their properties may not be as symmetrical as once believed. This opens a door. If neutrinos behave differently from their mirror counterparts, they could generate an imbalance in a sector of the universe that does not annihilate efficiently. That imbalance could later be transferred to ordinary matter through known interactions. In this picture, the universe does not create matter directly. It creates an asymmetry in neutrinos first, then translates it. The appeal of this idea lies in its subtlety. It does not require dramatic violations of known physics in the visible world. It relies on a hidden imbalance in a sector that is already elusive. But subtlety cuts both ways. Neutrinos are notoriously difficult to study. Their interactions are so weak that experiments must be massive, patient, and shielded deep underground. Even then, the signals are faint. Statistical certainty takes years. This makes the hunt slow. Another possibility involves the forces themselves. The early universe underwent rapid transitions as it cooled. Forces that are distinct today may once have been unified. As those forces separated, the universe may have passed through conditions where symmetry breaking was far stronger than anything we see now. These transitions could have created environments where matter-favoring processes were amplified dramatically, then shut off as the universe continued to cool. In this scenario, the missing asymmetry is not hiding in particles we can easily access. It lived briefly during a cosmic phase change and left behind only its consequence. This idea is difficult to test directly because the conditions no longer exist. The universe has moved on. We are reconstructing a fire from its ashes. That reconstruction depends on theoretical models and indirect constraints. Physicists look for signatures that such transitions would leave subtle patterns, rare events, or limits on how the early universe behaved. The difficulty here is restraint. It is easy to build models that produce the right amount of asymmetry. It is hard to build models that do so without breaking something else we know to be true. Every candidate explanation must survive a gauntlet of tests. It must respect conservation laws where required. It must align with precision measurements. It must not predict phenomena that have already been ruled out. This process is unforgiving. Many proposed mechanisms fail not because they are wrong in spirit, but because they are too generous. They solve the asymmetry problem but create others in the process. This forces physicists into a narrow corridor. The missing asymmetry must be large enough, early enough, and subtle enough to leave no obvious contradictions. The hunt becomes a balancing act. There is also the possibility that the asymmetry is not missing at all, just misunderstood. Perhaps the known laws, when applied correctly under extreme conditions, produce the required imbalance after all. Perhaps assumptions about equilibrium, timing, or interaction strength are slightly off. In that case, the problem is not new physics, but incomplete modeling. This possibility keeps the search grounded. It reminds physicists to exhaust what they already have before reaching for what they do not. Still, as years pass and experiments tighten their constraints, the sense grows that something genuinely new may be required. Not a dramatic overthrow of physics, but an extension, a deeper layer. What unites all these efforts is a shared recognition. The asymmetry that made the universe possible is not obvious. It does not dominate everyday physics. It reveals itself only under rare conditions, at extreme energies, or through painstaking precision. This makes the hunt psychologically difficult. There is no single target to aim at, no guaranteed discovery waiting at the end of a tunnel. Progress comes in small exclusions, incremental refinements, and long stretches of apparent stagnation. Yet this is how fundamental physics often advances. The absence of easy answers is not a sign of failure. It is a sign that the question is properly posed. The universe is not obligated to explain itself conveniently. As the hunt continues, the focus sharpens. Each failed explanation narrows the possibilities. Each new measurement trims the space where the missing asymmetry could hide. Over time, ignorance becomes structured. This structure matters because it tells us something important even before the answer arrives. It tells us that the universe did not leave its imbalance lying on the surface. It buried it deep, in places that require ingenuity to reach. The missing asymmetry is not a loose thread. It is woven into the fabric of early cosmic history. Finding it will not just explain why matter exists. It will reveal how the universe behaves when pushed to its limits, when symmetry is optional, equilibrium is fleeting, and outcomes become irreversible. The hunt is not about filling a gap in a textbook. It is about understanding the moment when existence stopped being symmetrical and started being historical. That moment is still out there, encoded in the universe's past, waiting to be decoded, and until it is found, the story of why anything exists remains deliberately unfinished. Once antimatter was confirmed to be real, a new question became unavoidable. If the universe can make antimatter so easily, so naturally, then where is it now? Not in laboratories, not in fleeting particle tracks, but on cosmic scales. If matter and antimatter were created in comparable amounts at the beginning, then regions of antimatter should still exist somewhere in the universe today. Entire domains, antigalaxies, antistars, vast structures built from the mirror of everything we see. And if such regions existed, they would not be subtle. Wherever matter meets antimatter on large scales, annihilation follows. Not quietly, not invisibly, it would release enormous amounts of energy, producing distinctive radiation that could travel across the cosmos. The universe should glow with the evidence. It does not. This absence is not speculative. It is observational. Astronomers look for the unmistakable signatures of large-scale annihilation, specific patterns of high-energy light that would mark the boundaries between matter and antimatter regions. Those signatures are missing. The sky is quiet in the way that matters. This silence is not neutral. It is evidence. If vast regions of antimatter existed near regions of matter, their borders would shine. The universe would be stitched together with annihilation fronts. Instead, observations show a cosmos dominated by matter, with no clear signs of large antimatter domains. This narrows the possibilities. Either antimatter was never abundant on large scales to begin with, or it was removed so efficiently and so early that it left almost no trace. The second option is harder to accept than it sounds. Annihilation releases energy. That energy does not disappear. It propagates. It affects the surrounding environment. If antimatter vanished in bulk at later times, the universe would remember. It does not, which suggests that if antimatter was erased, it was erased very early before structure formed, before light could travel freely, before memory could persist. This pushes the problem further back in time. The question, where did all the antimatter go, becomes, why did it never get the chance to stay? This distinction matters. If antimatter never formed large structures, then the universe did not split into matter and antimatter regions. It became matter-dominated almost immediately, long before galaxies or stars could form. That implies the imbalance was global, not local, not a patchwork outcome, but a universal one. The universe chose matter everywhere, all at once. This is a stronger claim than it first appears. A local imbalance could arise from chance fluctuations. One region might tip toward matter, another toward antimatter. Over time, these regions would grow apart as the universe expands. Annihilation would occur at the borders, leaving behind separate domains. But observations rule this out. The absence of annihilation signatures tells us that matter did not win in some places and lose in others. It won everywhere. That uniformity deepens the mystery. How does the universe coordinate such a preference across scales larger than any signal could have traveled at the time? How does an imbalance become coherent across the entire observable cosmos? This pushes explanations toward processes that operate before ordinary notions of distance and separation apply, toward eras when the universe was small enough, dense enough, and connected enough that a global outcome could emerge. It also eliminates comforting alternatives. We cannot hide antimatter beyond our observational horizon and claim ignorance. Even if large antimatter regions existed far away, their absence nearby still demands explanation. Why would matter dominate locally while antimatter dominates elsewhere? Why would the boundary fall exactly beyond what we can see? Physics prefers fewer coincidences. The simplest reading of the evidence is also the most unsettling. The universe did not allow antimatter to survive in significant quantities at all. Not here, not elsewhere. That conclusion forces a shift in perspective. Antimatter is not missing in the way a lost object is missing. It is missing in the way a cancelled possibility is missing. It existed briefly, then was systematically erased or never allowed to accumulate in the first place. This raises another uncomfortable point. If antimatter vanished early and completely, then the universe today carries almost no direct memory of it. We reconstruct its role from theory, from laboratory experiments, and from what didn't happen. This is a negative detection problem. We infer antimatter's absence by the absence of its consequences. This kind of reasoning is powerful but fragile. It relies on confidence that we know what antimatter would do if it were present. It assumes our understanding of annihilation, radiation, and cosmic evolution is solid, so far, that confidence has held. Every search for cosmic antimatter has come up empty-handed. No anti-nuclei drifting through space. No anti-galaxies lighting up the sky. No gamma-ray signatures betraying large-scale annihilation. The universe behaves as though antimatter lost decisively and early. This leads to a sobering realization. Antimatter is not the mirror world we might have imagined. It is not hiding just beyond our reach, waiting to be discovered. It is a fleeting participant in cosmic history, allowed to exist only briefly before being suppressed. This does not diminish its importance. It intensifies it, because something capable of erasing antimatter so thoroughly must have been powerful, pervasive, and precise. The mechanism did not merely tilt the balance. It prevented antimatter from ever claiming territory. This returns us to the core problem from a new angle. It is not enough to explain how matter survived annihilation. We must explain why antimatter never built anything comparable in the first place, why it never formed stars, why it never formed galaxies, why it never left scars on the sky. The silence is not accidental. It is structured, and that structure points backward, toward an early universe that was already biased in a coordinated way. The absence of antimatter is not an afterthought. It is a constraint that any successful explanation must satisfy. This narrows the field further. Any theory that produces matter locally but leaves antimatter elsewhere is disfavored. Any mechanism that delays annihilation too long is inconsistent with observations. Any explanation that produces patchy outcomes fails the test of uniformity. The universe is not only matter-dominated, it is consistently matter-dominated. That consistency is the clue. It tells us that the asymmetry was not a late accident. It was baked in early, before separation, before structure, before memory. Antimatter did not wander off. It was outpaced, outcompeted by a universe that changed conditions faster than antimatter could respond. Where did all the antimatter go? It went nowhere. It was never allowed to stay. And that answer, unsettling as it is, forces the next question into focus. If antimatter was suppressed everywhere, all at once, then the mechanism responsible must have operated at the deepest level of cosmic history, where space, time, and matter were still negotiating their roles. That is where the final pieces of this puzzle must lie, not in the sky today, but in the first moments when the universe decided which side of the mirror would endure. By now, the mystery is sharply defined. Matter exists. Antimatter does not, at least not on cosmic scales. The known laws allow an imbalance, but not enough of one. The early universe must have done something decisive, and whatever it did left only indirect traces. This is where experiments come in, not as final judges, but as persistent interrogators. Modern physics does not expect a single dramatic measurement to resolve the matter-antimatter problem. There is no switch to flip, no hidden chamber to open. Instead, progress comes from asking the same question in many different ways, under many different conditions, and watching carefully for disagreement. The strategy is simple in spirit and brutal in practice. Measure everything that should be symmetric, and look for places where symmetry fails. Some experiments focus on decay. Certain particles exist only briefly before transforming into others. The exact pattern of those transformations, how often they occur, how fast, and in what combinations can reveal tiny preferences built into nature. These preferences are not obvious. They appear as statistical imbalances that emerge only after millions or billions of events. One decay happens slightly more often than its mirror. One path is favored over another by a fraction of a percent. That fraction matters, because if nature is willing to cheat even a little, it tells us something fundamental about how the universe operates under extreme conditions. Other experiments focus on oscillation. Some particles do not keep a fixed identity. They change flavor as they travel, slipping between states in a way that defies classical intuition. The details of these oscillations encode information about mass, symmetry, and potential hidden biases. If matter and antimatter versions of these particles oscillate differently, the difference could point toward a deeper asymmetry that played a role in the early universe. But extracting that information is painstaking. Signals are faint. Background noise is relentless. Experiments run for years, sometimes decades, to accumulate enough data to make meaningful statements. Progress is measured not in breakthroughs, but in constraints. What cannot be true is often learned faster than what is true. This narrowing of possibilities is not failure. It is refinement. Each experiment that rules out a class of explanations sharpens the remaining mystery. The asymmetry is not just missing, it is cornered. There are also experiments designed to test whether matter and antimatter obey gravity in exactly the same way. On paper, the answer should be yes. Gravity couples to energy, and antimatter carries energy just like matter. But physics has learned to be careful with should, if ritus. If antimatter responded to gravity even slightly differently, it would have enormous implications for cosmology. It could influence how antimatter behaved in the early universe, how it clustered, or how quickly it was diluted. Testing this is extraordinarily difficult. Antimatter is hard to produce, harder to confine, and harder still to observe without annihilating it. Even tiny stray fields can overwhelm gravitational effects. Yet the effort continues, not because a difference is expected, but because the stakes are high enough to justify certainty. There are also experiments that search not for asymmetry itself, but for new particles or interactions that could generate it. These searches often look like fishing expeditions from the outside, massive detectors waiting for rare events that may never happen. But this patience is deliberate. If a new particle exists and plays a role in the matter-antimatter imbalance, it is likely elusive by design. It would interact weakly, decay quickly, or appear only under extreme conditions. Catching such a particle requires scale, sensitivity, and time. The absence of a signal does not discourage physicists, it informs them. It tells them where not to look next. This iterative process measure, constrain, refine defines the experimental side of the hunt. What makes it emotionally challenging is that none of these experiments promise closure. There is no guaranteed payoff. Each one could run its full course and still leave the central question unanswered, and yet they continue, because the alternative, accepting the imbalance as a brute fact, feels incomplete. Physics does not stop asking questions just because answers are hard. What unites these experiments is not optimism, but discipline. They are built on the recognition that nature does not reveal its deepest secrets easily. Precision must replace spectacle. Persistence must replace expectation. There is also a humility embedded in this approach. Physicists do not assume they know where the asymmetry hides. They design experiments that allow nature to answer in its own way. Even if the answer is not here, whoa, this humility is hard won. It comes from decades of surprises, false leads, and overturned assumptions. The experiments still asking the question do so without urgency. They are not racing a deadline. They are mapping ignorance. Each measurement is a negotiation with reality. Each constraint is a boundary drawn around what the universe allows. Over time, these boundaries form a shape. That shape is the outline of the missing explanation. It is tempting to imagine a future moment when everything clicks into place, a single result that suddenly makes sense of the imbalance and ties the story together. That may happen, but it is equally possible that the answer will emerge gradually, assembled from many small pieces that only form a coherent picture in hindsight. This is how fundamental understanding often arrives, not as revelation, but as accumulation. The experiments continue not because physicists are confident they will succeed quickly, but because they are confident the question is real. Matter exists. Antimatter does not. The laws we know are not enough. Something happened, and whatever happened left fingerprints subtle enough to survive billions of years without being obvious. Finding those fingerprints requires patience on a scale that mirrors the universe itself. In this sense, the experiments still asking the question are participating in the same story they are trying to explain. They are slow, incremental processes unfolding over time, shaped by constraints, accumulating irreversible results. They are the modern echo of the early universe's decision-making phase. Back then, conditions changed too fast for symmetry to catch up. Today, conditions change too slowly for answers to arrive all at once. The imbalance that made existence possible is being investigated with the same restraint that allowed it to endure. And as long as the experiments continue, the question remains alive, not answered, but not abandoned. The universe has not yet finished explaining itself, and physics is still listening. At the end of this story, there is no triumphant solution waiting to be revealed. There is only a fact: you exist. And by every clean, symmetrical rule the universe could have followed, you should not. Everything that makes up your body, every atom, every molecule, every organized structure traces back to a failure, not a dramatic collapse, not a catastrophic error, but a subtle deviation so small it barely registered at the beginning. A glitch, not the kind that breaks a system completely, but the kind that slips through unnoticed and changes everything downstream. In a perfectly balanced universe, matter and antimatter would have cancelled without remainder. No stars, no planets, no chemistry, no observers wondering how it all began, just radiation thinning into darkness. That universe would have been mathematically elegant. It would also have been empty. Instead, reality took a different path. Somewhere in its earliest moments, the universe failed to be perfectly fair. The mirror cracked. Equilibrium broke. Annihilation outran itself. A residue remained. That residue is not symbolic. It is literal. Every proton in your body belongs to that leftover. Every electron orbiting it does too. You are not built from the universe's main event. You are built from what escaped it. This reframes what it means to exist. You are not the natural outcome of symmetry. You are the consequence of its violation. The universe did not design you. It allowed you. That allowance is fragile. It depended on timing, imbalance, and conditions that no longer exist. The early universe had one chance to get it wrong in just the right way. Too much symmetry, and nothing remains. Too much chaos, and structure never forms. What survived sits between those extremes. This realization removes comfort and replaces it with something quieter. Existence is not guaranteed. It is permitted. The glitch that made matter possible did not aim at life. intelligence, or meaning. It did not anticipate planets or questions. It simply failed to erase everything. Everything else followed. Stars formed because matter remained. Galaxies assembled because gravity had something to work with. Chemistry emerged because atoms persisted long enough to combine. Life arose because complexity had time. At no point was this inevitable. The universe did not build upward toward you. It stumbled forward with leftovers. And you are part of what accumulated. This perspective changes how scale feels. Human concerns often shrink when set against cosmic distances and times. Compared to galaxies billions of light years across, individual lives feel insignificant. But insignificance misses the point. The fact that anything complex exists at all is already extraordinary. You are not small in an indifferent universe. You are improbable in a universe that almost erased itself. That improbability is not mystical. It is physical. It is encoded in the imbalance between matter and antimatter, in the broken symmetry of fundamental laws, in the fact that the universe did not remain reversible. Time gained direction. History accumulated. Consequences stuck. You exist because the universe stopped undoing itself. This also reshapes the idea of meaning. Meaning does not have to be granted from outside. It can emerge from contingency, from the fact that something fragile persisted against erasure. If existence were guaranteed, it would be trivial. The fact that it was conditional gives it weight. The cosmic glitch does not diminish you. It situates you. You are part of a universe that did not follow the most straightforward path. A universe that contains bias, history, and irreversibility. A universe where outcomes depend on moments that cannot be repeated. That makes awareness remarkable. Not because the universe needed it, but because it allows reflection on the fact that it almost chose otherwise. The atoms in your body were forged long after the initial imbalance was locked in, but they carry its signature. Without that early asymmetry, stars would not have formed. Without stars, the elements heavier than hydrogen would not exist. Without those elements, chemistry would remain simple and lifeless. Every layer of complexity rests on that first failure to cancel. This is not a story of triumph. It is a story of narrow survival. The universe did not select for observers. Observers emerged because the universe failed to erase all possibility of observation. That failure is the deepest common ancestor of everything that followed. When you look at the night sky, it is tempting to feel dwarfed by its size. But size is not the relevant metric. Persistence is. The universe is vast because matter survived long enough to spread out, collapse, ignite, and reorganize. That survival traces back to a deviation so small it still resists complete explanation. You are not just in the universe, you are evidence of its imperfection. And that imperfection is not a flaw to be corrected. It is the reason anything can exist at all. Physics continues to search for the mechanism behind the imbalance. Experiments refine constraints. Theories propose possibilities. The explanation may come one day, or it may remain incomplete. But regardless of how much we uncover, the fact remains unchanged. Existence depends on imbalance, on the universe not doing what symmetry alone would demand. This is a humbling realization, but not a despairing one. It suggests that reality is not optimized for elegance. It is shaped by history, contingency, and irreversible decisions. Those qualities are often associated with life itself. The universe is not a static object governed only by timeless rules. It is a process, and, like all processes, it carries the marks of its past. You carry those marks too. Every breath, every thought, every moment of awareness is made possible by a glitch that occurred before time had fully learned how to flow. The universe did not guarantee your existence. It allowed it, and that allowance is rare enough to matter, not because it makes you special in a cosmic hierarchy, but because it makes existence itself something that did not have to happen. The universe almost erased itself. It did not.